Chapter 5, Part 2, Metabolic Energy System. We're going into the aerobic system. This is page 196, Aerobic System, 196, Part 2. Aerobic system. Aerobic exercises requires the body to take oxygen from the atmosphere, deliver it to the lungs, transfer it into the blood, and pump it to the working muscles where it is used to oxidize carbohydrates and fats in order to produce ATP. The energy pathways is often termed the oxidative oxygen system and involves several body systems, including the respiratory, cardiovascular, muscular, and endocrine system. Through a complex series of chemical reactions, glycogen and fats are broken down in the presence of oxygen to provide energy to be transferred to ATP. During rest in light, low-intensity activity, the energy required for muscle contraction comes almost entirely from the aerobic production of ATP. During rest in light, low-intensity activities, the energy required for muscle contraction comes almost entirely from the aerobic production of ATP. Most cells, including muscle fibers, contain mitochondria, which is the site of aerobic ATP. The greater the number and the volume of mitochondria, the greater the cell's aerobic energy production capabilities. During prolonged exercise, more than 99% of the energy required is generated by aerobic reactions. These aerobic pathways provide the major supply of energy to all cells of the body through the metabolism of circulating glucose, stored fats, and stored carbohydrates. Because the amount of stored carbohydrates is limited, one of the most important adaptations to training is the shift by the body from the use of carbohydrates, stored fat, as a primary fuel source. Because the amount of stored carbohydrate is limited, one of the most important adaptations to training is the shift by the body from the use of carbohydrate to stored fat as primary fuel for energy. When the muscles are being used aerobically, they use both fat and glucose to produce ATP. The aerobic system produces much more ATP than the anaerobic system and gains far more ATP when using fat as a fuel. This is primarily because of the ability to convert fat, which yields 9 kcal of energy per gram, while glucose and protein yield only about half, 4 to 5. Additionally, the waste product of aerobic ATP production are water and CO2, which are both easily processed by the body, making aerobic energy production the more efficient method of generating energy and averting muscle fatigue. Which are both easily processed by the body, making aerobic energy production the more efficient method of generating energy and averting muscle fatigue. Page 197, anaerobic energy system. Anaerobic metabolism is the ability of the body to produce energy by metabolizing carbohydrates in the absence of oxygen. With increasing exercise intensity, the cardiorespiratory system makes every attempt to increase its delivery of oxygen to the mitochondria of the exercising muscle fibers to produce enough ATP aerobically. At some point in increasing intensity, the cardiorespiratory system becomes unable to supply enough oxygen to the exercising muscles, and energy production fails to meet energy needs, meaning the body has to increase its reliance on the anaerobic system to produce the ATP rapidly enough to meet those needs. The intensity level at which oxygen supply is unable to match the energy demands is referred to as anaerobic threshold. It has also been termed lactic threshold. Even though these terms are often used interchangeably, true lactic threshold occurs when anaerobic before true lactic threshold occurs before anaerobic threshold. In brief, the lactic threshold is termed by the serial blood analysis and increasing intensities of exercise, while anaerobic threshold can be determined through submaximal VO2 testing. While the measurement of oxygen consumption requires some technical expertise and equipment, it is still practical in an exercise science setting due to its ease of use versus the understandable reluctance of athletes to have repeated blood samples taken. The anaerobic system has high power, achieve energy quickly, and a limited capacity, but not for very long. The primary fuel for anaerobic ATP production is glucose stored in the muscle and the liver as glycogen, a large molecule made up of chains of glucose. This energy pathway is often referred to as the glycolytic or lactic acid system. During muscle contraction, stored glucose is broken down into lactic acid. During muscle contraction, stored glucose is broken down into lactic acid. It is estimated that if glycolysis was the sole source of fuel for exercise, one could only continue for maybe a minute. A second source of anaerobic ATP production is creatine phosphate. Very high power, but very low capacity. The CP molecule is also a high energy compound. Once the ATP has been split and its energy released from mechanical work by the muscle, the energy in the CP molecule can be quickly transferred to the used ADP, and a free phosphate molecule is attached, making a new ATP. This energy pathway is often referred to as the ATP-CP site system. As with the muscle store of ATP, there is an extremely limited supply of creatine phosphate. If this was the sole source of energy, exercise might be sustained for about 10 to 15 seconds. At no time is only one system functioning. All three systems are supplying energy constantly. The prominent system depends on the duration and intensity of exercise as seen in Table 5.1. In skeletal muscle, this little cycle goes on constantly at the myosin cross bridges and must be constantly resupplied by ATP from glycolytic and aerobic energy system sources. The main advantage of the ATP-CP system is the speed at which energy can be supplied, its power. The main drawback is that not as much ATP can be produced as with the aerobic system, limited capacity. The main drawback is that not as much ATP can be produced as with the aerobic system. If glycolysis is the prominent source of ATP, the result is an increasing level of lactic acid waste that can inhibit exercise. Lactic acid inhibits exercise. These anaerobic energy pathways are the main source of energy for high-intensity, short-duration activities. Lactic acid is continuously being processed and removed, produced and removed, even when the body is at rest. When lactic acid is produced faster than it's removed, it spills out into the blood, and symptoms of fatigue become evident. A major goal of training should be to minimize lactic acid production while enhancing lactic acid removal during exercise. One way to accomplish this is through a combination of high-intensity interval training and a prolonged submaximal training. Interval training helps maximize cardiorespiratory adaptation and increase VO2 max. The more oxygen consumed, the lower the reliance on the anaerobic, especially glycolytic breakdown of carbohydrates. Prolonged submaximal training can help to induce an increase in mitochondrial structure and function. These adaptations will help reduce lactic acid formation by increasing the fractional utilization of fatty acids as a mitochondrial fuel source, while facilitating lactic acid removal. These adaptations will help reduce lactic acid formation by increasing the fractional utilization of fatty acids as a mitochondrial fuel source, while facilitating lactic acid removal. Early work in exercise physiology was directed at determining the metabolic demands of different sports. Sports performance professionals who design workouts for athletes can use Table 5.2 to understand which system supplies the most energy, as well as which system probably needs the most training emphasized of competition. No sport is dependent on a single energy system, so each sport needs to focus on all energy systems during training. The relative training fraction devoted to each system can be estimated by using data from these types of tables. An example of this might be an athlete starting to jog on a treadmill going 7 miles per hour. After the first step, the muscles have to increase the rate of ATP to produce the required energy for the new physical demands at the demands of the 7-mile pace. In the transition from rest to light or moderate exercise, oxygen consumption increases rapidly and reaches a steady state within 1 to 4 minutes, depending on age and level of fitness. The fact that the VO2 does not increase instantaneously to a steady state value means an anaerobic energy source has to contribute to the overall production of the ATP at the beginning of the exercise. At 7 miles an hour, energy demand of the first steps, well before a steady state is reached, is the same as the last steps, well after attaining steady state. So the body has to get energy from somewhere while aerobic system catches up. So the body has to get energy from somewhere while the aerobic system catches up with its production of energy. At the onset of exercise, the ATP-CP system is the first active bioenergetic pathway that gives way to glycolysis and then finally to the aerobic energy production. After a steady state is reached, the body's ATP requirement is The body's ATP requirement is met via the balanced delivery and use after a steady state is reached. The body's ATP requirement is met via the balanced delivery and use of oxygen using aerobic metabolism. Energy needed for exercise in sports is not provided by any single bioenergetic pathway, but rather from a mixture of several metabolic energy systems that overlap based on the intensity and duration of work.